Hi everyone, my name is Ted Cross and I'm a technical advisor with Novi Labs. Today I'll be presenting our paper predicting water production in the Williston Basin using a machine learning model. Why should you care about accurate water forecasts? Well, disposal costs of between 50 cents and $2 a barrel means that water production can significantly impact well economics. But it's not just that. Lack of disposal capacity in some rare instances could force well shut-ins. You can flare gas, but you can't flare water, and sometimes trucking the water offsite just isn't an option. Additionally, produced water injection can cause issues such as induced seismicity or drilling issues driven by increased pressure in overburdened rock that's sitting in a shallow injection zone that's drilled through on the way to the target. Overbuilding or underbuilding water handling facilities and infrastructure can significantly increase costs, from the wellhead out to the regional networks. And produced water is toxic with high total dissolved solids, heavy metals, and radioactivity, depending on which basin you're in. And so proper handling of that produced water is critical to environmental and local stakeholders. So why use machine learning for this topic? Well, oil forecasting has improved with advanced statistical methods like machine learning, but water forecasting often uses simple approaches like applying a gridded water-oil ratio to your oil forecast, or just kind of a simple basin-level trend extrapolation. And why is that an issue? Well, in the Bakken Three Forks, on the right here, I'm showing you average oil production and average water production for 90-day cumes going from wells drilled in 2012 through the end of 2018. And you can see that originally in the play, it started off as the wells producing more oil than water, and now water production is higher on average than oil production for 90-day cumes. And the reason this is going on is that there's complicated interactions happening between larger completions designs, tightly spaced wells, changing geology to step outs, etc. And machine learning is excellent at dealing with those tough variable interactions, and so that's a great reason to apply it to this problem. For our model input data, we used our data is from the Bakken Three Forks play in the Williston Basin. The source is all the data is from the North Dakota Industrial Commission. They have a really high-quality publicly available data set, and so that's why this is just restricted to North Dakota rather than any data from Montana or Canada. For input variables, for completions, we used proppant and fluid values as well as stage counts. For spacing, we calculated distances to various neighbors, like closest and farthest of lateral neighbors, stacked neighbors, etc. We have timing variables like the number of parent wells, how long those parent wells have been online, and distances to parent wells. And for geology, we included a variety of well logs, mud log gas measurements, and structural tops. A couple things we didn't include: operator. Operator as a categorical variable tends to cluster a lot of other variables with it, since those operators will have a couple completions designs that they use. They'll be operating in a geographically concentrated area, so that is excluded. We also excluded latitude, longitude, county, or area, just preferring to focus on the geology. And then we don't have any post-drill operational data. At some point with the right database, we'd love to include that. For model training, we used a decision tree-based modeling approach, extremely random trees, or ETR. And the way it works, if you look over on the right, I have a kind of a schematic or cartoon tree of how decision trees would work for one of these models. You start off with all the data in one big pile, and that has a certain production average value. In this case, I have 90,000 barrels, 1 year cume. The data is then split by the tree according to one of the input features. In this case, we have water saturation, we have greater than 25% and less than 25% there. Then you split the data further and further into subgroups, by things like completions parameters or spacing parameters. And what you're left with at the end in these terminal leaf nodes are sets of wells that have average production values that are different than what it started off originally as. And so as these models are building their trees, they're looking for variables that are predictive. They're looking for cutoffs that are predictive, that can essentially discriminate between higher and low producers of oil. And they do this across an ensemble of thousands of trees. They can have a lot more layers than what we're showing here, ranges of different variables, etc. And so what the result is that you have a very predictive model that's essentially following a standard analog type curve based process, but at computerized speed. I do want to note that our models predict a 24-point vector of cumulative production going from 30 to 720 days rather than just a single point estimate. This allows us to get the shape of the curve in addition to just a single point estimate. And then we use Shapley values to kind of explain how the model is coming up with its predictions, and we'll spend a lot of time on that in some more detail later. So next up, looking at model training and performance. The way that we approach this is that we split the data randomly into 80% training data and 80% test data, and you can see the distributions of those two groups on the left and the right side of these set of two maps. On the right, I have the median adjusted percent error, so that's or absolute or adjusted. Those are it's going from 0 out to 720 days. That's essentially just how the production, how our prediction compares to the production values divided by the actual values. So you can see kind of through time, almost all the wells start off with higher error in the earlier days. It kind of stabilizes, and for the most part, our error is consistent across the life of the well, or consistent across the years, rather. So aggregating that all up, on the well level, our test group, we get to just under 25%, maybe about 23% median adjusted percent error. On the pad level, it's about 12%. So pretty happy with those error scores with what we're getting there. All right, Shapley values, or Shap values. Shapley values, this actually comes out of game theory, is where the original theory for Shapley values comes from. They're named after a guy named Lloyd Shapley, a mathematician, actually. And the idea is that they explain how much each variable contributed to the model's prediction. And let's unpack this in a little bit more detail. You can imagine that the simplest model you could use to make a prediction for a well is to average all the production profiles. So if you have no other information and you need to make a guess, you would just use the average. But as you learn more about each well, you can move that prediction away from the average by a certain amount of barrels of water in this instance, by knowing, for instance, hey, yeah, this water was completed with a lot of proppant. So that can inform the prediction that you make. And so each variable that goes into the model will have a different impact. And if we go over here and look on the left of this chart, we call this a Sharpnado chart. It's similar to a tornado chart that you may have seen from other Monte Carlo simulation outputs or other sensitivity style outputs. And for the Shap value chart, every dot here represents one well, and we're looking at Shapley values for IP720 here. And each kind of row here is a different feature or variable that went into the model. The kind of zero line here at the middle of the chart, that represents no impact, 0 barrels on the model prediction. To the right, you have a positive impact on the model prediction, and to the left, you have a negative impact. So let's go back up to the top here and look at the fluid per foot. That's showing up at the top. It has the broadest range, so that feature is having the largest impact on the model prediction. The dots are colored by the feature value, so red means that is a high value for that feature. So high values out here for fluid per foot, that's large fluid loading, is responsible for positive water production. So it's a positive correlation. The spread kind of represents the data density. So where you have the wide part of the clouds there, that's you have a lot of data. So we can see fluids ranked as the most important in the eyes of the model, then proppant, and we have one of our geology features, GeoPCA4, and then stage length, which you see has an inverse correlation with production. So if we take the Shapley values for each of those different input geology variables, the GeoPCA variables, we can add them together to get essentially what the model thinks is the most water-prone rock or the least water-prone rock. So the total geologic contribution to the water production is what this water Geoshap represents. We have a whole paper on the process for how we derive Geoshap, starting from raw logs top to geochem. You can go look it up and take a look at it in more detail by following that kind of title over there on the left. But the summary is that this map is showing you essentially a rock quality index, but it's not quality for producing oil; it's quality for producing water. And in dark green, we have the least water prone, so that's most oil prone. And on the far right, we have the most water prone rock. You can see the model; it's actually able to pick up things like the Ness and anticline in the partial Sainish field. So great to be able to see the model pick up on that in terms of areas of expected low water production. You also generally you're seeing the highest expected water production around the fringe of the play. You can also see the Three Forks generally has higher expected water production than the Bakken. Especially looking at like this area here, just to the west of the Nessa and one of the deeper parts of the basin. Three Forks is a lot of migration is impacting it. So you're in a deep part of the basin. All the oil's migrated up, and you're left with some water there. So I'm going to use these Geoshap for water values or water proneness index in some of the next charts here that I'll be showing you. So here we have water production sensitivity to completions as measured by Shapley values. On the left, we have a cross plot with a completions fluid in terms of barrels per foot. So we're going from 0 out to 60 barrels per foot. And that's cross plotted with the Shapley value for the completions fluid. And on the right, we have the same thing, but for proppant and proppant's Shapley value. You can see a couple things here. Number one, the total magnitude of the spread is greater for the completions fluid than it is for the proppant. That's the same thing that we saw when we were looking at the Sharpenato plot, going from 0 out to a large design where you're hitting the point of diminishing returns. You're getting plus 17 barrels of water per foot compared to plus 10 barrels of water per foot, and that's 720 cubic barrels of water. Just again as a reminder. There's also some other neat things that you could see here when we're cross-plotting it, or rather when we're including the color by the water values here, or the water Geoshap values. So in dark green, you have the most oil-prone rock, and in the dark blue, you have the most water-prone rock. And something interesting you can see here, kind of overloading your rock with water loading, you see about what's that? Maybe 4 barrels per foot difference between the response you're getting back from the high fluid or from the water-prone rock versus the oil-prone rock. Whereas for that in the high proppant scenarios where you're overloading your proppant value, you're getting a lot more actually back from that water-prone rock. And I think what this is showing is the model has basically learned that where your rock is really highly water saturated, if you're increasing that permeability by propping open your fractures, you're going to be producing more water. And if you're in an oil-prone area down here, you see that you're barely producing any more water as you go out there from let's say 1,000 pounds per foot up to 2,000. Whereas that same trend from 1,000 pounds per foot up to 2,000, if you're in a very water-prone area, you get big increase in your Shapley values, showing big increase in water from the completions. If we look at stage spacing compared to the other two completions parameters, we see that in general it has a much more muted impact than either the fluid or the proppant loading in the eyes of the model. It's only about 6 barrels per foot, going from very wide stages out there to tight stages. So not a surprise. It's generally thought to be less important than the other two for oil production, but interesting to see that nevertheless. So next we'll look at spacing and also the interactions between spacing and fluid loading on production. So here we have, on the x-axis, we have the number of wells per section going from 1 out to 12. And for anyone not super familiar with the Williston, it is done at a wider spacing, developed at a wider spacing than the Permian. Your rock's higher permeability. You only have 2 zones really that you can develop in most of the basin. 3 in some rare cases, but that's why you kind of topping out up there at 12 and greater. And on the y-axis we have the spacing Shapley values, and you can see, and this again in terms of 720 barrels per foot, but you can see these at 1 here. These are parent wells, standalone parents actually specifically. These have higher overall water Shapley values compared to the other wells. You get a big impact compared to the average. And then if we look over here at the tight wells, you see those are showing higher water Shapley values than the more widely spaced wells. But the other interesting thing here you can see, and I've broken out these 2 wells, or these two average lines here by the total completions barrels per foot. So in dark blue I have the average of wells that were completed with greater than 15 barrels per foot, and then in the gold we have wells that were drilled and completed with less than 15 barrels per foot of completions fluid. So you see an interesting divergence in between the Shapley values for tight wells with lots of fluid and tight wells without all that fluid, and you can see that you're seeing an increase in that water production from the combination of those two things, which is not a surprise. You have a lot of water production going into a small area. So next we'll take a look at competitor surveillance using Shapley values to kind of explain the operator's water production. And let me take a minute to walk through this. So again, on the x-axis we have IP day going from 0 out to 720. And then on the y-axis we have barrels of water versus average. And in black you have that operator's average water production compared to the basin average water production. So black here, or positive, that means that they are producing more water than average. Negative would be that operator is producing less water than average. And here we have EOG, Hess, Liberty, and Petro Hunt. And in blue I have these bars are representing that water's average completion Shapley values for water. So positive would be that their completions are in the eyes of the model contributing to higher water production. A negative would be the completions are contributing negatively to the water production compared to the average well. Red, you have the geology Shapley values. So both EOG and Hess are in rocks that are not very water prone, whereas Liberty and Petro Hunt are rocks that are on average more water prone. And finally, in purple, we have spacing, which on average is showing less impact than the other variables. So you can kind of see here just kind of how different operators, both these two operators with oil prone rock, these two operators with water prone rock, how differences in completions and spacing decisions can result in really large differences in average water production. And so, returning to the question from the very beginning on what has driven that average basin water increase, and here I have that same up and to the right trend of water production through time, 90-day cubes. I've incorporated the average basin Shapley values here for completions, geology, and spacing. And you can see that the blue bars, you start off, big time negative, and then you swing to a big time positive through time, with the average well in terms of completion size, on average, probably being drilled in late 2015, with smaller wells before that and larger wells after that. But that's responsible for the majority of the increase there in that basin average production. However, interesting thing to note here is that in the purple and in the red, that you're seeing that geology and spacing are starting to show a larger impact on those predictions. So that's probably a result of step outs and tighter spacing density, but that's pretty interesting to see. So wrapping it up, this machine learning model that we've built, it accurately predicts water production on a blind holdout set, 23% MAPE. We found that completions fluid loading is the most important feature for explaining water production. Fluid and proppant loading interact with geology in different ways. Excessive proppant loading in water-prone rocks will result in additional water production. Tight wells are associated with higher water production, especially when they're completed with higher fluid loading. We do see that completions explains most of the increase in average water production in the basin, even though geology and spacing are increasing in importance over the last couple of years. And then finally, and this is what I want to leave you with, and that's the software communities and oil and gas operators have spent a lot of time developing advanced techniques for forecasting oil production, and those techniques can be adapted for forecasting water production or for forecasting gas production, which can improve the accuracy of forecasts and also just improve generally operator understanding of why water is increasing, what are the main drivers for that water production, so that the various stakeholders who care about water production, proper handling and disposal of water, can understand the choices that they have to impact that production. So thank you for listening. Feel free to send us any questions that you have about the paper. Thank you.